Hey everybody, I wanted to spend a little time with you today talking about formal charge. And formal charge is really, when you're dealing with covalent compounds, it's kind of taking covalent compounds and bonding and Lewis dot structures to the next level. And so kind of what we've already learned is kind of the straightforward, the thing that works 95% of the time. The other 5% of the time, you need to kind of use these formal charges and things and these other tools in your toolkit to make sure that it works. And also, as you can see, let me get rid of my face here, but you can see that I have kind of changed around. I'm going to try a black background, okay? And I'm going to see how this works for this video. But let's talk about formal charge. Okay, and so formal charge is kind of like the charge on an atom in a covalent compound. Okay, now I say that because let's see if I can get my pen to work. There it goes. Okay, and so I say that because when we're dealing with this, we're not talking about like sodium plus, where this guy has an absolute dedicated charge because it's lost an electron. What we're dealing with is things like what the charge around, what the potential charge would be around the atoms, and I think that nitrate is this, okay, and then you put it in brackets and you put a 1 minus there. Okay, so this is kind of the, so it basically what we're saying is that this guy has a formal charge, there's that word, that kind of isn't a dedicated charge like this, but is different than what the number of valence electrons are. So all of that to say, and I think this will make much more sense when we do this example problem here, but we need to know the Lewis dot structure in order to calculate formal charge. And when we calculate formal charge, that's what FC stands for, okay, not like football club. Okay, we take the number of valence electrons that an element would have normally when we look at the periodic tables, the column that it's in. Okay, then we're looking at the number of non-bonding electrons plus half the bonding electrons. So for something like these singly bonded oxygens, they should have the same formal charge. And so I'll put, look, single bonded oxygen. And so the formal charge, the number of valence electrons in oxygen is 6, minus there's 6 non-bonding electrons, and there's plus, well, there's 2 bonding electrons because a single bond has 2 bonding electrons, and so half of that is 1. So 6 minus 6 plus 1, keep your parentheses in there for order of operation, that equals, well, 6 plus 1 is 7, so 6 minus 7 is a negative 1. Okay, so each of these has a formal charge of negative 1. Negative 1, I'm going to kind of just put it there with a little circle around it, because that's the formal charge, that's not a dedicated charge. Okay, now we'll look at the double bonded oxygen. This one is a different structure, but oxygen still has 6 valence electrons. And then around this it has 4 non-bonding electrons, plus 2, because that's half the number of valence electrons. You could also look at this as the number, you could say plus the number of bonds. That may help. Either one of those is correct. Okay, and then that equals 0. So this has no formal charge. And now with the nitrogen in the middle there's only 1 nitrogen. So again, nitrogen has 5 valence electrons. That's how many it normally would have. And then we do minus how many non-bonding electrons, which are none, and then the number of bonds are half the number of bonding electrons. Either way we think about it, we come up with 4. So 5 minus 4 is equal to a plus 1. Okay, so now we have plus, negative, negative. Now you'll notice that the formal charges will always add up to the overall charge on whatever it is that we're doing. So if what we're looking at. So if it's an ion, the sum of the formal charges will add up to the ion total. The other thing that we need to keep in mind about formal charge is that molecules want to have the structure that has the smallest formal charge, meaning the smallest number of atoms with a formal charge. And not only the smallest number of atoms with a formal charge, but also the smallest magnitude of formal charge. So it's +1, +2. If this were +2, that would be bad. Okay. And so when we think of making Lewis structures, we have to make Lewis structures on some of these more complex guys with formal charge in mind. Okay, so that's kind of how you calculate it. But let's move forward here. Okay, and then we say, it says what the most negative formal charge goes on the most electronegative atom, and then we go through the whole thing because this is negative. Whoa, hurt. You get to see the where I'm going with this, but okay. Electronegative, that's wanting a negative charge, and that formal charge is how many electrons that element has above and beyond its normal number of valence electrons. And so it would stand to reason that the most electronegative elements are going to have the formal charge. So let's draw the correct structure of hypochlorite. Okay, so hypochlorite is Cl. Now this isn't a lesson on Lewis dot structures, but we can, so there's 7 and 6 plus 1, so there's 14 electrons. Okay, and so do the central ion, 1, 2, so there's 2, 4, 6, 8, 10, 12, 14. Okay, and then we could put these in brackets, and we're going to put a 1 minus there. Now, in the past, we would look at that and we'd say, hey, that's great. Maybe that's the correct structure. Okay, but let's look at this based on formal charge. That oxygen here has 6 minus 6 plus 1, and so that's a formal charge of -1. The chlorine has a formal charge, let's see, 7 minus 7 plus 1. Okay, and so now this has a formal charge of, let's see, minus, oh, this is 6 plus 1, so that's formal charge of 0. See, even I can get screwed up here. I'm not perfect. Nobody's perfect. So that's 6, 2, 4, 6 plus 1. Okay, so that's a formal charge of 0. So that looks like a good structure, but we could also have an alternate structure of this guy where we have Cl. Okay, let's see here. How are we going to do this? Okay, we're going to put a double bond in here. Okay, that doesn't have enough electrons, so we're going to do that. Oxygen can expand its valence, but but chlorine can. So let's see. This looks funny, but let's figure it out here. Okay, so this is oxygen has 6 minus 4 plus 2, so that now has a formal charge of 0. And then chlorine in this structure has 7 minus 6 plus 2, which is a -1. So in this structure, the chlorine has the -1, and in this structure, the oxygen has the -1. So we have a choice. Which structure is the most correct? Well, in this case, this structure is absolutely the most correct because the negative charge is on oxygen, which is the more electronegative atom. Okay, so now that we've done this, now we can move forward and we can say what's the most valid Lewis dot structure for each of these. Okay, so sorry that this video is a little longer than most, but it's good to go on. So we've done sulfate ion a lot, okay? And so we would normally do sulfate ion kind of in the past like this, okay? And again, this isn't a video on how to draw Lewis structures. If you need that, you can go back and look at that. And so we would normally do this, okay? And then we would do the, notice all the oxygens are the same. So its oxygen is 6 minus, let's see, so that's going to be 6 plus 1, that's going to be -1. So each oxygen has a -1. Okay, now the sulfur is going to be 6 minus 0 plus 4, which is a +2. So now what we have here is every atom has a charge, has a formal charge, and that's what we don't want. So I'm going to go here and I'm going to see if we can draw some of these things and watch what happens when I do. Okay, I'm going to get rid of one bond or one electron pair, and I'm going to move it in the middle. Remember, oxygen can't expand its valence, so it's stuck having 8. Sulfur can expand its valence. It can have more than 8 electrons, so that's pretty cool. So here's the neat thing. This oxygen, these 3 oxygens still have the -1. The sulfur now has this +5, so this becomes a +1, which is better than the +2, and then the last one, and then this double bonded oxygen is 6 minus 4 plus 2, and now that is a 0 formal charge. Hey, a 0 formal charge, that's really awesome. Okay, so is there another way that we can limit formal charge again? Well, absolutely. What I can do is I can take another pair of electrons and I can come and I can make a double bond here. So now this oxygen, these oxygens are still going to be a formal charge of -1. These oxygens are going to be a formal charge of 0. But now look at what happened to the sulfur. The sulfur is 6 minus 0 plus 6, and that's a 0 charge. So the best structure for the sulfate ion is this guy right here with the multiple bonds there. And that's all determined by formal charge. What we're saying is that the sulfur has no real extra electrons floating around it. It has kind of the 6 that it normally would have. So we could do the same thing with the thiocyanate ion. So let me just do it this way here. Okay, and maybe the way to do this is to pause the video, try it yourself, see what you get, and see if you can come up with something. But let's go over this. And when you have 3 atoms in a row, it's usually bonded the way that it's written. Okay, so this is 5, and this is 4, and this is 6, plus another 1. So that's going to be 16 electrons. We've used 4, so we have 12 more. 2, 4, 6, 8, 10, 12. Okay, so we notice that the carbon doesn't have enough electrons, so we have to make a multiple bond. Okay, so multiple bond. Well, there's a lot of options here for us to do this. We could make a multiple bond here, like this, and like this. We could do it the other way, where we have a triple bond this way, and a single bond here. Or we could split it down the middle. Let's see, 1 minus, put the charge on here, 1 minus. Or we could split it down the middle, and we could do N double bond C double bond S. And then we have 2 electrons, 2 electrons, 2 electrons, 2 electrons. And then we can do 1 minus. And so, and this is why this is going to take a little while, is because now we have to calculate formal charge. Okay, so formal charge on nitrogen, in this case, the nitrogen is 5 minus 6 plus 1, and that formal charge is -2. So my guess is already that is a bad one because we don't want a whole ton of formal charge. Okay, so now let's look at this nitrogen. Okay, this nitrogen is equal to 5 minus 2 plus 3, and that's 0. Well, that looks really good. Okay, and now this nitrogen over here is equal to, let's see, 5 minus 4 plus 2, and so that's -1. So that looks good, and this one looks better, at least for now. This one we're just going to get rid of, okay, because we know that we have better options. Okay. So that was good. So now the options are, is it this guy or this guy? Well, let's look at the sulfur. On this side, the sulfur atom is 6 minus, and then this is a pair of electrons. So that's going to be 6 plus 1, and that equals a -1. Okay, and here the sulfur equals, I know it's messy and sloppy, okay, because it has 6 valence electrons, minus 4 plus 2, this is equal to 0. So the difference is this has a formal charge of 0 and this has a formal charge of -1. Here, this has a formal charge of -1 and this has a formal charge of 0. The carbon is going to be the same because it has 4 bonds and 4 bonds, so it's not going to change the formal charge of carbon in this case is going to be 0 in both atoms. Okay, but let's take a look. Which one is going to be the one that is the correct structure, or the most reasonable, most valid Lewis structure? Well, it's the one where the formal charge is on the more electronegative atom. And the more electronegative atom in this case is sulfur. Okay, we look at the periodic table, we find that sulfur is the most electronegative. And so here, okay, is the correct structure. So this is the most valid Lewis dot structure. So that wraps up everything about formal charge, kind of going deeper into covalent bonds than you probably ever wanted to know. But there it is, and have a great day.